In this video, I want to start talking a little bit about the properties of the Legendre polynomials. So the Legendre polynomials are solutions to this equation right here, this Legendre equation, such that if we plugged in for y some Legendre polynomial, they're often represented like this with a p, a large p with a subscript n, and it's a function of x. And so if we wanted to solve this equation, we would use the Frobenius method, which I showed in great detail in the previous video. So we would want to find some function that looks like this. So we go from n equals 0 to infinity, a n, and then x to the n. And so we would use that Frobenius method, which I'm not going to go through here. If you are interested in how that works, you can check out my previous video, so Frobenius method. And then we would end up with indicial equations that look like this. So a naught m times m minus 1 equals 0, and a1 times m plus 1 equals 1. So we have roots are equal to 0 and 1. And so what we have, we can obtain the coefficients. Once again, this would all be obtained through this Frobenius method, but I'm just going to sort of skip over doing all the sort of algebraic work here and just cut right to the chase. Minus a to the n, so we can get a of n plus 2 in terms of a sub n, and that will be p minus n times p plus n plus 1 over n plus 1 n plus 2. And so we can get we can get some coefficient 2 above this coefficient in terms of this coefficient. And what that ends up being is we can get our even coefficients will be equal to minus 1 to the nth. So that tells us essentially that it's just going to be alternating between minus and plus, because minus 1 to the 0 is 1, minus 1 to the 1 is minus 1, minus 1 to the second power is plus 1, and so over the summation we just sort of get alternating plus and minus. So that's all that is telling us. So a naught, and then we get this large fraction here times p minus 2 times p minus 4, continuing on to p minus 2n plus 2 times p plus 1 times p plus 3, and then that goes on and on until we get to p plus 2n plus 1, I think. You might want to check me on that. That might be a minus 1. But anyway, I can probably draw a better line than that. So this is a fraction, and in the denominator we will have 2n factorial. And the odd coefficients, so a 2n 2n plus 1, will equal minus 1 to the nth times a naught times p minus 1 times p minus 3, and that will continue going until we get to p minus 2n plus 1 times p plus 2 times p plus 4, going on and on until we get to p plus 2n. And that will be over 2n plus 1 factorial. So these here are just the ways that we get the coefficients for our coefficients for our power series, the power series that we had up here. So this is the power series that we the sort of general form of the power series that we started with. We said that our solution is going to look something like this, and we're just finding these a sub n's here. And these are how we are going to find it. And these p's here, these p's are the same p's that we see up in this original equation up here. So if you just substitute, say, p equals 0 in here, then that would be having 0 in the p's up here, for instance. And so that's just where all of that comes from. And if if these p's are integers, then we will end up getting a polynomial. So once again, the difference between a polynomial and a power series. So a power series is of the form a summation from n equals 0 to infinity of a n x n, and a polynomial is of the form summation from n equals 0 to some finite n of a n x to the n. And so a power series can go on, well, it does go on to infinity. A polynomial terminates at some n. And if these p's are any kind of integer, if they are a positive integer, then we get a polynomial. And that polynomial will be of the form, so it will be of the form y equals from r equals 0 to 1/2 p. And I'll explain that here in just a second. So a of p minus 2r times x to the p minus 2r. And so this little half p here is just telling us that this r goes up to half of whatever p is. So if we were looking at p equals 6, then r would go from 0, 1, 2, 3. So the r would just go up to 3. So we would end up, as you can see here, the lowest power would be p minus 2 times 3. Well, I said that p was 6, so we can put a little 6 in here. So that's 6 minus 6, which equals 0. So that is our lowest power. Whereas if we had 6 minus 2 times 0, that obviously just equals 6. But we can see that this is multiplied by 2, so we are going to go in multiples of 2. So for instance, if we had 6 minus 2 times 1, if we put 1 in for r, then we can see that that is 4. So if if so if p is an even number, then we can see that we're going to have powers of 6, 4, 2, and 0. So we would be 6, 4, 2, and 0, or actually no, it'd be the other way around. 6, 4, 2, and 0. But anyway, we see that we just go through evens, where if we made p odd, then it would be, then we would just have odd powers. But anyway, this is the form that our solution is going to take when we have p as integers. Um, and so I guess if you wanted to show this a little more explicitly, we could have it be something like apx to the p plus ap minus 2x to the p minus 2 plus a p minus 4x to the p minus 4, and that will continue on until we get to a p minus 1/2 p times x to the p minus 1/2 p, or or uh, or p 1/2 r rather, 1/2 r. Um, and so yeah, this is sort of the general form of how it'll look. And what we will end up getting, so if we write in our a sub p minus 2r, so I guess up here, since we have 2r, so this would be 2 times 1/2. So we would end up getting, these up here would be a sub p minus, so 2 times 1/2 of p would just be p, and x to the p minus p. So obviously that is a naught and x to the 0. So that is what this up here should look like. But anyway, our a sub p minus 2r is going to be equal to minus 1 to the r power. So once again, that's just alternating minus and plus. That's all that is telling us, times a sub p, and then we will get something that looks like 2 times 4 times 6, going all the way up to 2r, and then we will have that multiplied by 2p minus 1 times 2p minus 3, and that will keep going until we get to 2p minus 2r plus 1. So that is our denominator here, and up here in the numerator we will have p times p minus 1 times p minus 2, going on until we get to p minus 2r plus 1. And so I thought about going through a bunch of the sort of algebra, but I think once again I'm just going to cut to the chase. This numerator up here, we can sort of manipulate until we get it in the form of p factorial over p minus 2r factorial. This part right here we can get to look like 2 to the r power times r factorial, and this part right here we can get to look like 2p factorial times p minus r factorial over 2 to the r power times 2p minus 2r factorial. And the reason to do all this is so that we can get this in a form that looks like this. So we will have y equals a sub p times the summation from r equals 0 to 1 half p, and that will then have minus 1 to the r times our p factorial over p minus 2r factorial. So that was this up here. And then we multiply that by 1 minus 2 to the r times r factorial, which was this right here. And we see this is in the denominator because that was in the denominator. And then we multiply that by well, essentially this right here, but sort of flipped around since that is in the denominator. And so that will be 2 to the r times 2p minus 2r factorial times p factorial all over 2p factorial p minus r factorial. And then we have our x to the p minus 2r. Because remember, all this is just our coefficients. And so after doing some canceling out of terms on here, what we get is y equals a sub p summation from r equals 0 up to 1 half p of minus 1 to the r times, and so this will simplify down to we have r factorial times p minus 2r factorial times p minus r factorial times 2p factorial, and that is under p factorial to the second power times 2p minus 2r factorial times x to the p minus 2r. And if we set a sub p equal to 2p factorial over 2 to the p times p factorial squared, then what we can do is simplify this even further, so that we now have our p, and I've been using p, so I'll put a little subscript p there. This is our Legendre polynomial, is equal to the summation from r equals 0 to 1 half p of minus 1 to the r, and that will be times 2 to the p r factorial p minus r factorial times p minus 2r factorial, and that is the numerator will be 2p minus 2r factorial, and then that is times our x to the p minus 2r. Okay, so that was a lot of sort of moving symbols around. So we ended up getting this, which is what we use to sort of generate our Legendre polynomials. And so I actually went through and just did this for p equals 4. I did that. I was going to go through it sort of writing it down here, but instead I just took a picture of my notes here. And so I just substituted in 4 for everywhere there was so everywhere there was a p, I put a 4, and for r I just well, I did the first term here, then I put 1 in for r down here, and then 2 in for r down here. Remember, r is going up to half of p, so it only goes up to 2. But anyway, for the first term up here, we have negative 1 to the 0th power, which will just be 1. But then I did the 2 to the 4th and the 0 factorial. So 2 to the 4th is 16. 0 factorial is 1. 4 minus 0 factorial is 24. And 4 minus 2 times 0, which is just 0, is also 24. Then up here, 2 times 4 minus 0, which is 8 factorial, is 40,320. This minus 1 to the 0 was just 1. And x to the 4 minus 2 times 0, which is just 0, 4 minus 0 is x to the 4th. So I went through, I multiplied everything in the denominator. I ended up with 40,320 over 9,216 times x to the 4th, which simplifies down to 35 over 8 times x to the 4. And I will just write that up here, 35 over 8 x to the 4th. So that is our first term. So then I did the second term down here. So plus, that's minus 1 to the first power, which is just a minus 1. Once again, so now I just did this for r equals 1. So that so this 0 just became a 1. So that ends up giving us 720. And then all this down here, 2 to the 4th is 16. 1 factorial is 1. 4 minus 1, which is 3 factorial, is 6. And then 4 minus 2 factorial is just 2. And then 4 minus 2 times 1 is 2, so x squared. We end up getting this 720 over 192 x squared, which gives us 15 fourths x squared. If we want to give that a common denominator with our first term, that is 30 over 8x squared. And that should be a minus. I should have a minus sign in here because remember we had that negative 1 to the first power, which makes it a minus. So we have minus 30 over 8x squared. So I will write that in up here. Minus 30 over 8x squared. And so then I just did the same thing over here, but for instead of, so I substituted r in for or 2 in for r. And so going through the same process, I ended up with this 24 over the denominator times x to the 0, because 4 minus 2 times 2 is 0. So I ended up with 24 over 64, which is 3/8. And it's a plus because our minus 1 squared is positive. So that gives us plus 3/8. And if we take out a common factor of 1/8, we get 1/8 times 35x to the fourth minus 30x squared plus 3. And so this is our P4 of x. So this is the polynomial of the fourth degree. We see if we look at the Wikipedia here, if we look at the fourth Legendre polynomial here, that's exactly what we get: 1/8 times 35x to the fourth minus 30x squared plus 3. And so using this formula that we got here, using all of this up here. So we started, as I said, with this second order ordinary differential equation up here. I said that the solution, the function that satisfies this, will look something like this x to the m times this power series. I used the Frobenius method, got our roots of 0 and 1. Then I went through all of this to get our formulas for the coefficients, and then going through all of this, so getting so say we said that if p was a positive integer, that it would become a polynomial, and it would be a polynomial that looks something like this right here. So it would look something like this right here. And using that with our formulas here for the coefficients, we ended up going through all this sort of symbol manipulation to get this formula. And so using the fourth p, so the 4 for p, and then summing through with the r's, we were able to get the fourth Legendre polynomial. And so so this formula up here will give us the Legendre polynomials, but there's also this thing called Rodriguez's formula, or Rodriguez's formula, which is so the pth, or whatever number you want to put in for the p there, whatever order of polynomial you want, is equal to 1 over 2 to the p power times p factorial multiplied by the pth derivative of x squared minus 1 to the p power. And so once again, I went through that using our fourth degree here. So I put 4 in for all the p's, so 2 to the fourth and then 4 factorial. But then we had to take the fourth derivative of x squared minus 1 to the fourth power. So here I just did the first derivative, which gives us, of x squared minus 1 to the fourth, which just gives us 8x times x squared minus 1 to the third. Then I brought this down and took the derivative of that to give us the second derivative, which gave us 8 times x squared minus 1 squared times 7x squared minus 1. I brought this whole thing here, so I guess I should have extended that arrow down to here and brought that in here, just to not have to write it all again. And so I took the derivative of that, and that gave me 336x to the fifth minus 480x to the third plus 144x. Then I took the derivative of that, which would give us the fourth derivative. That gave us 1680x to the fourth minus 1440x squared plus 144. Then I brought that over here, so I took our 1 over 2 to the fourth times 4 factorial, which is 1 over 16 times 24, or 1 over 384. So I multiplied that into our fourth derivative here. And that gives us 1680 over 384 times x to the fourth minus 1440 over 384 times x squared plus 144 over 384. And once again, that gave us this right here, which is exactly this is exactly the fourth polynomial, the fourth Legendre polynomial. Remember up here, then we just took out that factor of 1/8, and that gave us the fourth Legendre polynomial. And so these are sort of the two ways that you can get the Legendre polynomials. You can do it from all this, which we got from our Frobenius method of solving this this up here, this particular second order ordinary differential equation. And that ended up giving us this formula right here. And so then you can also use this Rodriguez's formula. So I'm not going to show how to get from this to this or this to this. I'm just showing that these are two valid ways of getting the polynomials, the Legendre polynomials. And so, for this p here, you could plug in any number and it'll give you a Legendre polynomial. And so these right here, so I'll zoom in a little bit. These are the first 10 Legendre polynomials right here. So if you put, so see this has a little n down here, but I was using p. So I was, so the first version, or if we have 0 for n, or in my case for p, so putting a little 0 right there, we would get 1, then x, then this 1/2 times 3x squared minus 1, so on and so forth. And so these are the graphs of the first 6 of these polynomials here. And so that's between -1 and 1, which is where these are convergent. But anyway, that is just a little bit about how these polynomials sort of come about. They come about essentially from solving this second order ordinary differential equation. And that gives us our Legendre polynomials, which in the next couple of videos we will see are the things that we need for spherical harmonics. And so this is how it will tie into the Schrödinger equation. And so that's kind of where all this is going, what this is all leading up to. But anyway, I hope this was at least somewhat enlightening to you. I think, I mean, this is just sort of the first groundwork of just showing where these polynomials come from. So in the next couple videos, I'm going to talk a little bit more about the actual properties of these polynomials. So I will see you in the next video.